All right, so welcome back. So hello, scientists of all ages, and I'm going to say it in Spanish as well, which is my native language. Hola, científicos de todas las edades. Please do study mathematics in both languages, especially in Texas. I'm delighted to talk about my favorite topic, robotics, which happens to be also my main activity most of my days. How wonderful. And I'm hoping to motivate people here of all ages to explore this vast field of science and engineering. Welcome to my talk on humanoid of the future. As a kid, I read a lot of manga comics and Isaac Asimov books. I also got my first PC, like many of you, when I was in middle school, even on those times. I started loving both computation and the physical sciences, which are chiefly combined in humanoid robotic systems. At that time, robotics sounded like an unconventional technology that combined a couple of really cool things. In one hand, artificial intelligence. On the other, physical mobility, which hopefully could help us in our daily lives. I was absolutely certain that sooner or later, human-centered robotics would be a game-changing technology. And here in this image, we see that 15 years later, Dreamer, our robot, which many of you saw outside, meets UT Austin's president, Greg Fembes. How game-changing this is as an ambassador of innovation and robotic technologies at the University of Texas at Austin. I went on for a PhD in Stanford University in robotics, and I got very excited by a 2008 report by the National Intelligence Council, which actually attempts to predict the future, in particular disruptive technologies by the year 2025, so 17 years later. So really is trying to anticipate what's going to go on. And these are a list of the technologies that were predicted at that time. The first one is biogerontotechnology, which is the extension of human life, how important that is. Then energy storage, biofuels, clean coal technologies. If you're on those fields, now we hear about them all the time, but at those times, it was still fairly new to talk about them. But the fifth technology is service robotics, and I was very happy to see it considered as a game-changing technology. And in particular, the report stated that the development and implementation of robots for elder care applications and the development of human augmentation technologies mean that robots could be working alongside humans in looking after and rehabilitating people, but also warn that the change in employment would adversely affect lower-income workers. So we have to be very careful with these technologies, not only robotics, but computation, mechanization, transportation, and so on and so forth. They do change radically the way we do things. So please be sensitive about those things, embrace them, but with care. I also got motivated by another report from the European company Fatronic, which showed that by age 70, 20% of the population suffers from mobility and manipulation problems. And this number, unfortunately, increases to 42% by age 80. Do we have to get sad? No, we don't. We need to think about life, what we call life after mobility, after we don't move the same way that we move today. And robotics can help out in several ways, in providing, first of all, wearable devices, things that we can put in our bodies that will make us walk again and cook our meals perhaps on our own. And second, elder care robots at home, robots that will take care of our loved ones when unfortunately we cannot be there. And that's another compelling reason to pursue research and ventures in human-centered robotics. With all this fuss, I became interested in the emerging field of human-centered robotics, which I define formally as a study of machines and robotic systems with high mobility to assist, augment, or represent humans in any way that will increase social comfort, productivity, security, and health. So the human is always at the center. We should not fear the robot. I guess that many of you do, but we should embrace it and have him help us. And because robotics are not really limited by the same energetics than humans, we can create systems with incredible capabilities, like this robot from the movie Robots a few years ago. It has arms, it has this anthropomorphic look and feel, it has legs, also it can move, but suddenly it can use its energy to do wonderful things like process things at home, for instance, or conduct chemical analysis, or go outside and do many complicated things. And this is precisely what we attempt to do with human-centered robotics. And this leads to the question of what can human-centered robots do, and how are they going to cooperate with humans? While I was doing my research as a student, I worked with the Honda Motor Corporation for many years. And this is the vision that we share together, that of supporting humans in our daily chores to make us more productive and taken care of. Another area of human-centered robotics has to do with operating robots remotely, for instance, using our cell phones. The idea is that many laboratories like mine will produce these systems that are very expensive. And you saw one here outside. It's actually $500,000. But we don't want to be the only ones using them. We want schools like yours to use them. So we created a program called the Cloud-Based Advanced Robotics Laboratory, in which we connect students on the left here, teachers in this campus across the world to these devices. They can turn them on. They can teleoperate them. They can gather data. They can use them for their reports or for their high-end research. How wonderful it would be that these sort of programs, they happen for every single piece of machinery that is complicated and expensive in any university. It would be an incredible gift for everybody interested on those technologies. Fortunately, this project was funded by the Longhorn Innovation Fund for Technology of the Cochlear School of Engineering here on campus. And it led to this video fulfilling our vision. Let me play it. Okay, it doesn't have volume actually, but undergrad student of UT Austin, Bridget Owens, can control the robot with her cell phone. For this, we developed what is called a web framework, which many of you will end up working with this type of technologies. It contains a web server, a dynamic website onto which you display button simulations, webcams, all sorts of control processes, and a communication interface to actually control the machine. This technology allows us to ultimately teleoperate from Home Dreamer to clean up a table, for instance. You can see very clearly how this is going to be useful. It also allows us to take data and kind of analyze the impact of these movements that we are analyzing or we are producing. And this can be beneficial, for instance, in the classroom for teaching geometry and physics and control systems and programming and so on and so forth. It's really a very comprehensive type of system. Another area where humanoid robots will soon be used involves cooperating with humans in harsh environments. Here we have two amazing agencies on the left and on the right championing these efforts. Really, is happening. On the left, we have the Office of Naval Research, which has this vision of firefighting because it's very important for their core missions. And they do it but with casualties. Normally, typically, when there's a firefighting situation, there is a pair of firefighters working together. They want to substitute the person on the front that takes all of the danger, all the damage, but at the same time cooperates with the person on the back guiding the fire. There has to be a cooperation between a machine and a human. The machine needs to understand what the human wants, where you want to go. And the human wants to anticipate what the robot is going to do. Only by this kind of cognitive abilities or these cooperative abilities, this system can come forward and be useful. On the right side, we have NASA. NASA has here in Texas, in Houston, Johnson Space Center, very comprehensive program on going to Mars, exploring it with human mission. And for that, robots have to go first. And they have to build outposts and habitats and instrumentation. And ultimately, they have to fit in the same spaces than humans. So we cannot really sign up a large card-like robot because it's not going to go inside the same spaces. So humanoids are being considered very seriously by these agencies. A final goal of human-centered robotics is to figure out how robots can safely share our everyday spaces. And this is the vision that I produce and other people share, obviously, around. We want robots to transport things around. We have seen Amazon.com trying to use UAVs, and manned ground vehicles might become also very important. But what happens when they appear in this kind of a scene where there are kids over here? Do we have to perpetually try to avoid humans, or do we have to do what we call biomimetic behaviors, in which we actually copy what humans do? We are very comfortable engaging in contact. We can sense it, respond quickly, move together with a human. We investigate how robots can do these capabilities. Just wonderful. We don't want to avoid being secluded from humans. We want to share the same spaces or investigate those capabilities. Now that we've learned something about humanoids and human-centered robotics, let's talk about how can we make them move like humans. The picture on the left shows control points on the robot's body, such as the center of mass, which allows you to balance. When you move the center of mass, it has to be between your feet without falling. Control points include the legs for locomotion and the hands for manipulation. These are the very same points we use for control. We use something called Cartesian frames. If you are in high school, probably you have learned these things. X, Y, Z coordinates. We literally control those coordinates with control systems. We control them using a branch of mathematics called optimal control. Now, none of you in high school or middle school probably is doing optimal control, but you're going to face those things when you go into mathematical programs, into aerospace engineering, into mechanical engineering, into computer science, and so on so forth. This is fascinating. And here, I'm not going to go into details of the mathematics, but mathematics are so important especially if you are into describing movement, controlling movement, analyzing what's going on with the human motion, making biomimetic behaviors. Mathematics is the main communication language of us on that front. And this brings us to the next topic, which concerns the field of legged locomotion, walking robots. It's amazing. The Navy has actually a program focusing on cognitive robotics and human-robot interaction, and they're putting quite a bit of money. It's about $30 million worth yearly. They funded our laboratory a few years ago to explore locomotion of humanoid robots in a structured environment. So you can see here kind of this vision of entering this vessel that is on fire and going to these cluttered spaces and doing it in contact with humans. Now, I also want to advertise the Navy and how wonderful it is to work for the Naval Research Laboratory up in Washington, D.C. They have an S&T program, just wonderful. And high school kids, college students, they're very integrated. So if you are into these things, I completely support and encourage you guys to reach out to these places. For this project with the Navy, our focus has been on having robots walking over rough terrains and doing so with agility. Agility, we define it as the ability to change direction and speed very quickly. But we lack a general understanding or a scientific understanding of agility. What are the equations of agility? Give me the equations, sometimes I say, and I'll give you the behavior. We lack robots that actually move around like the American Ninja Warrior, or humans put them on and become superheroes. We lack applications, apps, like Google apps or iPhone apps that you download onto a robot and right away they endow these capabilities. A kid on house next to you has developed an application, you download it, and it works right away. But we want these things to happen, and these are the kind of things that we scientifically investigate. To illustrate agility, let's take the American Ninja Warrior competition. Wonderful if you are onto these things. How can we understand what these athletes are doing? How can we make robots do the same thing? And these are the very fundamental questions that we want to understand. And hopefully also transfer these skills onto machines, because we really understand them, machines can do them. We can have then our unmanned machines, or we can make machines for the human when later on, unfortunately, we cannot do these motions, but we want to regain them again. To explore these questions, a few years ago, we built Hume, this robot picture on the left side. It's an educational bipedal robot. It simplifies the human body to just 2 legs with simple point feet, but this is enough to move quickly in rough terrains. Hume weighs 15 kilograms. It's force control in the sense that you can touch it and it knows that you are there. It knows that you are touching it. This is wonderful technology. It moves at 15 radians per second. Now, if you are into degrees, radians is the international system equivalent of degrees, which is an orientation metric. 15 radians per second is very fast speeds. Probably speed runners run at these speeds, like Olympic athletes. It is unsupported. It means that you let it go, and it has to balance on these tiny point feet, like jumping stills. It's a very hard task. And it contains an array of sensors. It has feet contact sensors, the same as your Lego machines, for instance, but it also has something to know where you are in the environment. How can you know where you are in the environment? Sensors? What sensors? For instance, yes, you can have a kinet sensor, right? You can have UAV. How UAVs know they are in the space? How they know it? By GPS, right? But they also use something called inertial measurement unit. Inertial measurement unit, 7 satellites. These are something called accelerometers and also gyroscopes. Gives you velocity and acceleration readings. You integrate them, and if it has very small drift, you can actually estimate where you're going to be over time. So you need these kind of positioning systems to know what your pose is and where you are in space. There's a lot of computation going on. There is Linux systems, for instance, National Instruments. They develop their control boards, and inside some of them have real-time operating systems. We have also physics-based simulation that anticipate how the robot is going to move, and this is part of the software infrastructure. So robotics becomes a hard problem in part, and the kids here that work in robotics are really very courageous, because you need to know all of these things. You need to know the mathematics, the hardware, the sensing, the operating systems, and so on and so forth. Career robotics requires a little bit of patience, as many other careers. So how do we tell Hume how to walk? Well, here is a happy human walking in the same manner that we would like Hume to walk. How do we explain this behavior to the robot? Well, first let's use physics. What kind of simple physical object can represent humans walking? Let's suppose only one leg is in contact with the terrain. A leg is like a stick, right? And at the end of the stick, there is large bodies, which are similar to big balls. What model has a stick and a ball? Right? It's a pendulum, right? That's it. We use what we call the inverted, we reverted, right? The inverted pendulum model to represent the human model. And this has gone for ages, for 50 years, for rehabilitation, for robotics, we have used that simple model. Now, let's take away the human and consider the pendulum only. Well, pendulums are very well studied system in mathematics. Here, lower, I don't pretend to understand it, we show one of the standard equations of pendulums, which is called a differential equation. The double dots means acceleration. Accelerations are proportional to the distance between the center of mass and the position of the leg. This also means, if you integrate this equation, that walking implies that we're moving exponentially. We're accelerating exponentially. And this is why we fall so quickly. If we're walking and we have a stone on the ground, our acceleration is exponential. So we run around the room and fall on the floor. So these kind of equations allow us to understand these kind of movements, allow us to predict the trajectories of the robot accelerating and decelerating. And therefore, we can, with programs like MATLAB, we can simulate what an actual walking pattern is going to look. Now that we have the trajectories for a single step, how do we calculate multiple steps? So this is similar to a gymnast here on the right side, wanting to jump a vault, starting at an initial pose and finishing at a final pose. She has to mentally calculate when to touch the vault in order to perform the maneuver. Similarly, our computers calculate when to change the feet so we can climb the step on the rough terrain based on the pendulum trajectories that we showed earlier. We call this process motion planning. So this is one of the dimensions. Motion planning is the process of figuring out what to do to walk or manipulate or do whatever is useful for this kind of machines. Now, we're done, right? Well, no, we're not. Can we take these trajectories and directly download them to the robot to walk? And the answer is an absolute no. Why is the reason? What is missing? Balancing, but what we saw earlier is a way to figure out when to balance, right? Because the robot is not a pendulum, actually. It's close to a pendulum, but it's going to go somewhere else. Our predictions are a little bit off, right? So instead, we need to have something called robust control systems or feedback control systems, which constantly recalculate all the trajectories given the current state of the robot. So the field of control systems, the same that when you go to space, you have a rocket, it's constantly measuring and changing the thrust. The same thing happens here. With its own actuators, it's constantly correcting, recalculating, repositioning the next foot until it gets it right. And the result of all of this, when you get it right, all of these technologies, is that the robot can actually walk and support it. So let's see that. This is what can happen. We can now let this very delicate machine, and it figures out how to work on its own for a while, And we do what I call here experimentation, right? So a lot of hours in the laboratory, that's what we do. There's only 3 robots in the world that can do this with point feet. And ours is the one that has the smallest point feet, right? So we always have this thing that my robot is bigger than yours, right? It's kind of competition, right? All right. So now that we have understood locomotion using simple contact models, can we study locomotion using our entire bodies, your hands and legs? The problem is that the previous pendulum model was too simple. A few years ago, we developed what we call multi-contact models, which consist of a bunch of sticks connected to a big ball. We use them to represent whole body locomotion, similarly to tensegrity models, robots that we see here on the right side. And the nice thing about tensegrity models, these are technologies also developed by NASA, is that the equations of motion of these models are also well understood. So we can do the same process that we did with the pendulum model. We can now produce these very sophisticated locomotion behaviors. Why? Well, because sometimes we use our entire bodies. If we're going to go to the mountains, and we're having a device with us that actually allows us to go when we're old, it has to use hands and feet the same as children do it today. But we can also use it for scientific questions. We can use these new models to study, for instance, the movements of our primate ancestors. This is Lucy, a female hominid discovered in Ethiopia in 1974, and which lived about 3 million years old. And the question is, did she walk using her legs or or using hands and legs? Well, I don't really know. But we can analyze her motion using our tensegrity models. What's the simulation we have performed? I don't have sound. Is that correct? Is sound okay? Okay. So, my apologies. So here we simulate her movement in an environment with multiple tree-like branches. The simulation, which is MATLAB, by the way, performs the motions automatically. So we're not motion capturing or figuring out some hand. It is automatically, autonomously produced. And we can use the resulting data to prove scientific hypotheses about Lucy. And this is how scientific discovery can be done. We're connecting robotics to anthropology. Perhaps we can figure out where these ancient humans came from by analyzing those patterns. Did they walk? Did they live in the trees or not? Did they live in Ethiopia or live farther away? So it's just wonderful, all the dimensions of robotics. One of our dreams would be, in the end, to help the elderly and the impaired to regain their movement by developing wearable technologies we call exoskeletons. They can take them outside or even help them to play again with their grandchildren. Wouldn't that be a wonderful technology that we could accomplish with robotics? Absolutely, right? And there are already some commercial devices out there that are starting to accomplish these capabilities. These ones are from Honda Motor Corporation. It is expected that there will be a big market, so we're going to make money, right, on exoskeletons in the near future. So get ready to work on these industries when you are older, okay? When you get out of your school, you might end up developing these devices. Is there a question over there? You have a question? Yes? Well, that's a good question. So he's asking if these devices need to be bipedal. This is the field of what we call orthotic devices. And there's certainly a lot of possible combinations. And one of them is to have it for a particular part of your body. Absolutely. Yeah, that answer your question? Okay. Okay, so we have so far explored what can humanoid robots do and how they move like humans. Let's now explore how will humanoid robots in the future be like. And here are a couple of pictures of Robonaut, a robot by NASA in Arizona, which they use for exploring, building nothing else than outposts in Mars. It's just a crazy idea. When I started working with NASA, I was like, they're nuts, right? I'm never gonna really internalize these ideas. But fortunately, I spent a year and a half in Houston working with them, and I was completely brainwashed. So now I do believe it, and I pass this information to my students. I tell them, look, we're not doing a project for NASA. You're believing that we're building outpost in Mars. And this is a Texas technology. This is not like some crazy country, right? This is Texas, right? And this points to the future of robotics. To advance these kind of capabilities, thankfully, Obama announced the National Robotics Initiative a few years ago. It's a $34 million program yearly to accelerate the development and use of robots in the United States and work beside or cooperate with people. And that was done very timely because now we're competing and kicking something in the rear with the Koreans and the Chinese and everybody else. We are all friends, but we want the United States to do great on those areas. The first year the program was created, my laboratory proposed to the National Science Foundation a project in which robots would perform assembly tasks, building things precisely in rough terrains, not in the factory floor where everything is precise, but now going to the mountains, going to the unstructured factories, in your homes and so on, with the same level of accuracy. Some of the key questions were how to balance these robots when there's an object on the floor, how they're going to recover balance, how precisely they're going to do these manipulations, given they're not bolted to the ground and everything is not deterministic, how to manipulate the environment with the help of humans, how to learn with from the humans, how to combine and share the controls with the humans. We were delighted when we heard that our project was actually generously funded, but we were surprised at the same time when we heard that not NSF, but NASA was the funding agency. And the reason was because building outposts in Mars, this incredible idea by NASA, required the same skills, moving in rough terrains, manipulating the structured environments, communicating with the human, receiving commands, learning from the human. So we entered this project at full speed. To pursue this research in an educational environment like ours, we started building a Dreamer with a company called Meka, which now belongs to Google. A lot of these companies, by the way, they're now being purchased by big corporations. And we call it Dreamer, as I said, right? And here is the picture. In cartoon animation, there is a well-known concept. If you like cartoons, many of your kids, I'm sure you draw cartoons, right? And you have to make them, well, sometimes not, but sometimes you want to make them cute. So there is the science of cuteness of cartoons, right? Or the science of not cuteness, if you go the other side. And this is called the uncanny valley, which states that if you try to copy a human too closely, eyes, and when you draw a friend of yours, right? Normally, if you're not an expert, it ends up being pretty creepy, right? But if you simplify and exaggerate the traits of the face, it might actually look cute. We therefore look into one of my favorite cartoons, Nausicaa of the Valley of the Wind, to motivate the design of Dreamer's head. And I believe that it was a success. And of course, we used the University of Texas colors for the hair of Dreamer as a recognition for the incredible support of this university to these kind of programs. Now I'm going to embarrass my wife who's sitting here. Secretly, however, I had designed a head that looked a little bit like my wife. And I wonder how many people in the world do get this awesome opportunity to design a humanoid robot that looks like a relative or like your wife, right? So please do try it. Just wonderful. Building a humanoid head was a key decision. It attracted so much attention. And believe me, the robot didn't have a head for a year, and nobody stopped in my laboratory. We put a head on, and Michael Bay, the director of Transformers 4, was calling my laboratory for having Dreamer in the movie Transformers 4. She appeared within 30 seconds alongside actors Mark Wahlberg and Nicola Peltz. What a delight to participate in the motion picture industry, and entertainment, obviously, is another dimension of robotics, whether it is for special effects. Now we're going to see a lot of Star Wars. We have here R2-D2 somewhere here, right? Or whether you actually make machines for this industry. Something to consider, animatronics. Disney has an entire program in robotics. You can work with robotics, build robotic systems, and work for Disney. How a wonderful field. Another thing that you might consider when you finish your studies. But more importantly, Dreamer has become a symbol of innovation at the University of Texas at Austin. And the reason is because it combines many of the cutting-edge technologies that this university excels, and which includes areas like machine design, many of you will like, electronic systems, building these complicated embedded systems, artificial intelligence, which I think that even high schools soon will start to adopt these kind of programs, and cloud-based computing. There's going to be so many jobs in cloud-based computing, among many others. As students, I do encourage you to come to this university, become students, to become graduate or undergraduate students, to push our innovation much farther than we're doing here currently. So while working on Dreamer, a terrible tsunami, big wave after an earthquake, took place in Japan. I believe it was in 2011. The waves didn't destroy, actually, the nearby nuclear power plant. It just went over the 60-foot contention wall. But they cut off the power, and after several days unattended, the reactors blew up, causing $100 billion in damage. The US Defense Advanced Research Projects Agency, also called DARPA, thought that this could happen in our country too, and decided to create a challenge. Anybody? The DARPA Robotics Challenge, to see if humanoid robots could repair nuclear power plants. Now, this is crazy. When they throw it out, I was, it's nuts, this guy, right? It consisted of 8 challenges, right, in 2011, 2012, which included robots driving cars, just driving our everyday cars, right, autonomously, walking on rough terrains, just in any terrain that we normally go, removing debris from the ground, clearing areas, opening heavy doors, not just a door that you just move, but coordinating the forces, and it's complicated for us to move through a door. The same thing, climbing industrial ladders, breaking walls with tools. That was one of the craziest ideas. Closing valves and assembling industrial parts. We thought they were truly nuts and will never accomplish that. But sure enough, we still went on, and we teamed up with NASA Johnson Space Center to build the Valkyrie humanoid robot, a Texas production, which NASA anticipated to look like this fancy and sleek machine. That was before it was fabricated. Okay, in paper, you design your fantasy. We're all kind of laughing a little bit. Is this going to happen or not, right? So this picture shows actually the end result once we built it. Unfortunately, it looks like it gained a little bit of weight during the design process. But we kept its human-like good looks, okay? To make this happen, 4 people in my laboratory, including myself, moved down to Houston, Johnson Space Center, around Galveston for 15 months, and worked alongside a large and very talented NASA team. Unbelievable what kind of personnel we have there. We're literally locked in the room where the Apollo lander spacecraft was built in 1968 to go to the moon, and that's so inspirational. These walls were hosting those devices. It was super stressful, honestly. But what a great experience. So I do encourage you to sign up for these programs. And NASA actually liked very young researchers, some of them as early as high school. Maybe not for the full-fledged program, but for part of it. Our students at the University of Texas designed a unique actuator, the device that pushes this robot to be incredibly fast and these high payloads, which was able to generate a huge amount of force, but in a very small package, and that's a trick. You have a very small thing that can lift a bear, as my student says, and at the same time sense the forces of a human. So it has to be very delicate. You have to be able to touch the robot with a minimal amount of force and have the robot know about that. To our delight, it was immediately adopted by NASA for their rehabilitation program first. They have a rehabilitation program as well. Here we see these compact devices here built at UT Austin, used for rehabilitation, lower limb rehabilitation. People that have to exercise with a machine, which is also a huge market, by the way. Then it went on to be tested in the X2 MINA exoskeleton, which is a device that originally was designed for astronauts to do exercise in space. It forces them to move. But ultimately, it became an Earth device which allowed impaired individuals to regain movement. And you can see it here on the lower part because it's very compact and very power dense. And it turns out that our ankles, muscles, they produce the biggest forces for locomotion. It was a perfect application. We were delighted of seeing all these things happen. And eventually, it became the new actuator technology for various parts of the Valkyrie humanoid robot. In this movie, we show the process of construction of Valkyrie with a great participation by our lab. We're delighted to see many of our ideas taking place in this amazing humanoid robot. Our students went on and designed actuators, control systems, testing, software, interfaces of all sorts, human-robot interaction. You can see these actuators can sense the forces and respond to them and go on through an entire process of building a wonderful machine with very talented team at NASA. Let me just wait for a second here. You're going to see our actuator in a second. Over here. This is technology developed here at UT Austin. And NASA adopted it as one of the key technologies for Valkyrie for walking. So don't be discouraged. Push your technologies forward, and maybe we will go to really amazing places. Ultimately, we're able to develop not only the upper body and the lower body. I put it together and compete in the DARPA robotics competition, demonstrating Valkyrie's ability to remotely operate in a nuclear power plant setup. Another wonderful event for us. Don't get discouraged. You can accomplish these things as well. NASA also looked at our what we call whole body control software, large software architecture we developed. Here we show the infrastructure we built to control robots remotely, which includes a visualization tool. You see here this visualization on the left screen. It's called RVIS. It's actually what we call an open source visualization. A lot of this advanced software can now be downloaded and used by anyone. It displays the current state of the robot. Then using the head has actually eyes. It's not for beauty. It has actually lasers that allow you to reconstruct the environment with something we call a 3D point cloud. And this is transmitted over a low bandwidth communication channel and then superimposed with this simulation of Valkyrie. Kim, the operator, then single-handedly constructs behaviors using a software program that is actually similar to Scratch. Some of the programs perhaps you use. It's a visual program that constructs we call actions and motion planners, and you put them together, control sequences, and you construct a complete behavior. You simulate it, and once it works, you upload it to the robot, and the robot is going to perform it in the same way that we do it with robots in Mars. We simulate, upload, and then perform the behavior. So with a single hand, she's able to actually do this incredibly complicated behavior. This is how we control humanoid robots today. NASA really liked our work and awarded us the Elite Team Award for the design of Valkyrie. What a great honor from NASA. So again, ask for prizes, by the way, when you go to places. Hey, I did that. Give me an award. Don't be shy about it. Today, not without lots of effort and pain, I would say also, Valkyrie is a successful program where four humanoid robots have been built and given to various universities around the world. This picture is just a couple of months old. This robot is actually for sale, and people are buying it. The Department of Energy, universities in UK. It's just amazing that we were able to be involved in this project. This is a promotional movie of Valkyrie made by NASA last summer after they completed putting together the whole program, and really showcasing how awesome is American technology. You can see now all these actuators becoming alive and giving these kind of biomimetic behaviors. NASA has a lot of expertise in building hands. They look just like humans, and they also do hook 'em horns, right? And the robots, the legs that we develop with them, we can make them do these incredible things. It's really strong. By the way, it's a female robot, if you're wondering, right? So you can It's a bodybuilding athlete, right? He's in Houston, actually. Based on Valkyrie, NASA has created a new challenge competition called the Space Robotics Challenge, in which teams with Valkyries will solve problems found in space, such as building instrumentation and houses in Mars for human exploration. And US is going to become leader on these fields because of this program. What an incredible event. And as I said, NASA likes to enroll students at young ages. So do visit NASA, do apply for jobs. They have programs for high schoolers. They have programs especially for undergraduate students. It is good to start early with NASA. They don't like people my age anymore. I'm too old, right? They like to get 19 years old, 20 years old. This is at the age you have to go to NASA if you want to do a career. Just a wonderful place. There are many humanoid robots developed today, all of them for research purposes. Some of them belong to companies such as Google or Honda Motor Corporation. Will this type of robots become practical for commercial purposes? And in fact, the shape and form of a robot is not what is important. What is important is to provide new capabilities to solve real-world important problems. And if a human-like form factor is needed, then humanoids can be a solution. In that context, some of the areas in demand for human-centered robotics include exoskeletons for assistance and special operations. We have the Chancellor McRaven of this university, who was the head of US SOCOM, which is a Special Operations Unit, and they develop things for keeping this country safe and for peacekeeping. We want to support these operations. Urban ground reconnaissance and first responders. Nuclear material handling. The Department of Energy is trying to purchase a Valkyrie to go inside the facilities and do the same things that humans do, but in a safe manner. Firefighting for the Navy. Search and rescue. The Boston Police Department actually is interested on those technologies as well. Infrastructure maintenance, assisted living, orthotics, like this gentleman asked over there. These are the dimensions of human-centered robotics. Not all of them will look exactly like these humanoids, but an understanding of the very basic movements of humans will allow us to develop very effective devices. So as a conclusion, in the future, not too far from now, robotic technologies or robotic setups will look like this. Ready? There will be many more female researchers and students participating and leading great robotic projects. So please go ahead and sign up for robotics today.